Now we are going to start with a new law, which is very important law related to the conductivity, that is the kohlrausch law. You know that kohlrausch actually performed certain experiment which led to the formulation of this important law, that is the kohlrausch law, and it is going to prove very helpful because it has many applications, right, which we can easily use to calculate the conductivity of different substances we are going to see here. So you know that what kind of experiment he said or what conclusion he made actually. So you know what he did, he actually took, he just like again I am just going to tell you that what he did, he actually monitored many electrolytes. He actually monitored many electrolytes. He carefully observed those electrolytes. And you know that what kind of electrolytes he observed? He observed those kind of electrolytes which contain a common ion, like I will say NaCl and KCl. So these kind of electrolytes it actually took into consideration. As you can see, Cl is the common ion, right. Likewise we can have KBr and we can have KCl. So here we see that K is the common ion. So he actually took 3 to 4 you can say different electrolytes, but they were having the common ion, and he just monitored those electrolytes and came to the conclusion that if an electrolytes contain the same kind of ion, then the molar conductivity difference between the two, is same. Again, I am just going to explain you how. Suppose I have an example for you. Suppose I have electrolyte which have common ion, let's say KCl and NaCl. As you can see, Cl is the common ion. And if I talk about the molar conductivity of KCl, its value is 149.9 something. And if I talk about molar conductivity of NaCl, it is 126.5. So if I take a difference between the conductivity, it is just going to come 23.4. Right. Now I am going to take another electrolytes which will have a common ion like KNO3 and NaNO3. Here the common ion is the nitrate, and we have molar conductivities respectively that is 145 and 121.6. If I take a difference out of it, then again the difference comes out to be 23.4. Likewise, let us take another example. It's KBr and NABr, and if we take into consideration their molar conductivity is 151.9, 128.5, let us subtract them, let us take a difference, again it comes out to be 23.4. So that means he said that if you take an electrolytes which have at least one common ion, then both the ions should not be same. One thing I want to make you clear, only the one ion should be same. So if we take an different electrolytes which have one common ion, then what we observe actually, that difference between the molar conductivity of the two is always the same. As you can see that it was KCl and NaCl, the conductivity difference was 23.4. Here again it was KNO3 and NaNO3, again the difference was same, and same for KBr and NABr. So this led to the formulation of the kohlrausch law. So, and one more thing you need to remember here, see, if we talk about any electrolyte which completely dissociate, suppose I will take an example of AB. If it is a strong electrolyte, it will completely dissociate. Any salt or any electrolyte in general I will say, so it will completely dissociate. So in this case, the positive and negative ions have equal contribution toward molar conductivity. They have actually equal contribution towards molar conductivity. So this led to the formulation of, these whole conclusions led to the formulation of this important law, that is the kohlrausch law. So let's say, what does it state? It states that at infinite dilution, that when you add large amount of water to it, that means there is less concentration, then, and when the dissociation is complete, then each ion of electrolyte contribute towards the molar conductivity of the electrolyte, and even the conductivity is same, So this is what is the kohlrausch law. So that means if I need to express it mathematically, so I can write that molar conductivity of, let's say, KCl is equal to conductivity of K positive ions plus lambda Cl negative, that is conductivity due to chloride ion. So this is how you are going to state a mathematical expression for the kohlrausch law. So this is what is the kohlrausch law. Now it has certain applications, it is being used at many places. So let's see first that where we can use this kohlrausch law and how it is beneficial for us. So the first major application is that it helps us to calculate molar conductivity for a weak electrolyte. Otherwise, when we discussed conductivity, I told you that involves the Huckel equation, that it is very difficult to calculate the molar conductivity for a weak electrolyte, right? But it is made possible by the kohlrausch law that we can actually calculate the molar conductivity even for a weak electrolyte. See how we are going to calculate? Let's take an example. Let's see that I have acetic acid, that is a weak electrolyte, and we know that it undergo dissociation, but it gets partially dissociated, right. So if I need to write the molar conductivity of CH3COH, so I will write this contribution lambda this and by lambda this. Now how you are going to get the conductivity for this? So for this, take up 3-4 electrolytes which have the same ions, or you can say which have at least one ion common with CH3COH. Let's take few examples. Let's take NaCl. So molar conductivity for NaCl is conductivity by Na plus lambda Cl negative. Again, if I need to, so let's take another example, let's say that CH3COONA, then it is going to be conductivity due to CH3CO negative and conductivity due to Na positive. So as you can see that this electrolyte has a common ion CH3CO, CH3CO. Let's take another example, another common electrolyte. Let's say we took HCl, it also has a same ion. So it will contribute, this thing lambda will be H positive plus lambda Cl negative. So let's say that molar conductivity for NaCl is X, for this one is Y, and this is Z. Let us assume these values. So now how to find this thing? The first thing I think you're clear that you need to take a weak electrolyte, and for weak electrolyte we need to calculate molar conductivity. So I'm just going to write an expression first, and after that I'm going to take up let's say three electrolytes which will have common ions among them. As I took NaCl because it has Na similar to this, right, and Cl here was also this thing, and CH3CONH is a part of this weak electrolyte. So we are going to take two electrolytes which will not have a common ion. So let's say that like if we differentiate among them, so what two kinds of electrolytes are there which do not have any common ion? So it is this one and this one, right. So what we are going to do is we are going to add up. We are going to add the uncommon data. So by adding uncommon data, what do we get? We get lambda CH3CO negative, this, plus lambda Na positive, then plus lambda H positive, then plus lambda Cl negative. We are calculating the molar conductivity, right. Now after adding the uncommon data, subtract the third one which is left. So this is left, and it contains the ion similar to this and as well as to this, because this is the electrolyte which has a common ion with if we see a similarity with this also, we see a similarity with this also. So just subtract this from here. So we have minus lambda Na positive plus lambda Cl negative. Now if we write the values in terms of x, y, z, so we know that CH3C, we first took this equation, this is something y. So I'm going to write in place of this as Y. So now if I say see another one, H positive Cl negative, so value is Z, so that means I'm going to add up Z. Na and Cl is X, so let's subtract X from here. So how you will come to know that it is going to give the molar conductivity of CH3COH? So let's cancel the same terms. See, this is positive lambda Na and this is negative, so just cancel out. And we have lambda Cl negative again cancel out. So we are just left with this and this. And we know that for a weak electrolyte we have only this thing. So that means the lambda m here is for CH3COOH, because it depends upon lambda CH3CO negative plus lambda H positive, because we are just left with that only. So that means by following this method, that means adding the value for adding the molar conductivity value for the uncommon data and subtracting the other one, we are going to get the value for the weak electrolyte. So this is how we are going to calculate the molar conductivity for the weak electrolyte. So this is the first application. Let's see in second application. So the second application is that we can actually have the value for equilibrium constant. We can have the value for the equilibrium constant. So we have K is equal to lambda C, let's say that this is the conductivity, we will write C here. It is the conductivity for a particular concentration, right, and this is going to be lambda naught, that is the conductivity at infinite dilution or at zero concentration. We can write either of. So if we just put the values, what we get equilibrium constant is equal to we are going to put this value, and what is this value? It is kappa upon m, and by converting the units for the volume, and we have this lambda naught, and we can find this lambda naught by the kohlrausch law, and the rest you know that how to find. So this is the second application that we can find the equilibrium constant. How? We just had in this thing, that is the K is equal to at particular concentration, that is the conductivity at particular concentration to conductivity at infinite dilution. Putting this value, we have for molar conductivity we have K upon m into 1000. So this is what we can get it, we can solve for the K. Likewise, the third application is that we can actually find the degree of dissociation. Let's say suppose I have AB and it gets dissociated to form A plus B. Let's say at time 0 its concentration is C and their concentration is 0. So now if alpha is the degree of dissociation, let's say that at time t it gets dissociated to this thing and C alpha is formed. So if we write the expression for K, it becomes C square alpha square. This we have already done in equilibrium, right? So if you have any doubt, just refer to the equilibrium slide. So it is C square alpha square divided by C1 minus alpha. C cancels out. So K is equal to C alpha square 1 minus alpha. For infinite dilution, we just cancel this lambda. We are left with K C alpha square. So this degree of dissociation can be found as K upon C, root of K upon C. So but like this, you can actually calculate the degree of dissociation. So these are the three important applications we can use for the kohlrausch law. So I think it's clear that kohlrausch law is a law that just states that if you take a different electrolyte which are having a common ion, then molar conductivity difference for them is actually the same. We also proved that by taking an example. Likewise, it leads to the formulation that at infinite dilution there is an equal contribution of the, like if a substance get completely dissociate, then there is an equal contribution. So we can write the contribution as I told you, like if we have molar conductivity for KCl, and if it is a this thing strong electrolyte, we can write lambda K plus lambda Cl, because both are going to contribute equal in the conductance. So the applications we can find for the weak electrolyte, you know that how we are going to do it. We can find the equilibrium constant and also we can find the degree for the degree of dissociation. So these are the applications of the